This video will cover the topic using the rational zeros theorem to find all zeros of a polynomial, complex zeros. Let's first define the rational zeros theorem. The rational zeros theorem states that if p of x is a polynomial with integer coefficients, and if p over q is a zero of p of x, then p is a factor of the constant term of p of x, and q is a factor of the leading coefficient of p of x.
That sounds really confusing. What does that even mean?
That means that in order to find the rational zeros of a polynomial, we list all the factors of the leading coefficient, and these values are all the possible values of q. And we'll list all the factors of the constant, and these values are possible values of p. We will then list all possible p over q combinations.
So what do we need to do to find complex values if there are any?
We will follow the process in the using a given zero to write a polynomial as a product of linear factors complex zeros topic. If you are not familiar with polynomial long division, then it is a good idea to review this topic before watching the rest of this video. Let's work on an example. The function below has at least one rational zero. Use this fact to find all zeros of the function g of x is equal to 5x cubed plus 6x squared plus 36x plus 7. Since it is given to us that the function has at least one rational zero, we can use the rational zeros theorem to find a rational zero. So first what we will do is list the factors of 5 and the factors of 7. The possible values of p are the factors of 7, and the factors of 7 are plus or minus 1 and plus or minus 7. The possible values of q are the factors of 5, and the factors of 5 are plus or minus 1 and plus or minus 5. So the possible values of p over q are plus or minus 1 over 1, plus or minus 7 over 1, plus or minus 1/5, and plus or minus 7/5. Those values of p over q happen to be the possible rational zeros of g of x. Let's first solve g of 1. If g of 1 is equal to 0, then we know that positive 1 is indeed a rational zero of g of x. G of 1 is equal to 5 times 1 cubed plus 6 times 1 squared plus 36 times 1 plus 7, which is equal to 11 plus 36 plus 7, which we know is definitely not equal to 0. So we know that positive 1 is not a zero of g of x. Now let's try solving for g of negative 1/5. This is equal to 5 times negative 1/5 cubed plus 6 times negative 1/5 squared plus 36 times negative 1/5 plus 7. This happens to equal 0. So we know that negative 1/5 is a rational zero of g of x. Since x is equal to negative 1/5 then, since negative 1/5 is a rational zero of g of x, x plus 1/5 is equal to 0, which means that x plus 1/5 is a factor of g of x. Since x plus 1/5 is a factor of g of x plus 1/5 times a function q of x is going to be equal to g of x. In order to solve for q of x, we need to perform polynomial long division. Since 5x squared times x is equal to 5x cubed, our first term in q of x is 5x squared. Our second term of q of x is going to be 5x, since 5x times x is equal to 5x squared. Our final term of q of x is going to be plus 35, since 35 times x is 35x. And 35 times 1/5 is positive 7. If we subtract again, we get 0. So, q of x is equal to 5x squared plus 5x plus 35. Because g of x is equal to x plus 1/5 times q of x, g of x is also equal to x plus 1/5 times 5x squared plus 5x plus 35, since this is what equals q of x. So now, using the quadratic formula, we can solve for the zeros of q of x. Through using the quadratic formula, we get that x is equal to negative 5 plus or minus the square root of 5 squared minus 4 times 5 times 35, all of this divided by 2 times 5. This simplifies down to negative 5 plus or minus the square root of negative 675 divided by 10. This simplifies down to negative 1/2 plus or minus 3 times the square root of 3 divided by 2 times I. We have an I here since we took the square root of a negative number, which results in a complex value. And that's what this I here denotes. So, the zeros of g of x are negative 1/5, negative 1/2 plus 3 times the square root of 3 over 2i, and negative 1/2 minus 3 times the square root of 3 over 2i.
Okay, that makes sense. So we first find a rational zero and use it to find a real factor. Then we use polynomial long division to find a quadratic function q where qx times the real factor is equal to the original polynomial. After this we find all the zeros of qx, right?
Exactly.